All right, let's just jump right in. Welcome to today's Explainer, where we are embarking on a truly mind-bending journey. We're going to explore this massive, highly intricate mathematical library built entirely in the Lean-4 theorem prover. Now, if you're not familiar, Lean-4 is essentially a programming language used by mathematicians to prove that complex theories are absolutely undeniably true. But listen, this isn't just your standard collection of geometry proofs. No way. This project attempts to map out absolutely everything. We're talking everything from structural topology all the way to the very boundaries of metaphysics and existence itself. It's a formalist, computationally verifiable model of reality.
I actually want to start right here, with this quote pulled directly from the source code. Stillness is the vacuum state. No Kleinemann, zero entropy, no observable structure. The baseline of being. No Kleinemann, meaning absolutely no unpredictable swerves, no deviations, just perfect stillness. We're actually skipping a traditional agenda for this explainer today because I really just want to pull you immediately into the bizarre, highly formalist world we're about to explore. We're looking at a universe where abstract philosophical concepts, like the literal baseline of being, are being translated into hard, computationally verifiable code.
To give you an idea of the sheer scale we're dealing with here, take a look at this. This is just a tiny slice of the macro-scale topology and geometric structures directory. You've got file names like Boole, Kleinemann, Braid sitting right alongside cosmic infinity. It's visually overwhelming, right? But that's entirely intentional. The author of this library is systematically trying to categorize physical, theoretical, and metaphysical phenomena, all using strict topological frameworks. It's an incredibly ambitious, just staggering scope of work.
228. To really hammer home the size of this topological library, there are exactly 228 distinct files sitting in this directory alone. And they aren't just mapping one narrow specific domain. These files cover an astonishing range. They are mathematically formalizing everything from the categorization systems of the Dewey Decimal System, analyzing history and literature, all the way to deriving the critical dimensions of superstring theory. It's wild.
Section 1. The rules of the game. Strict computational formalization.
So, to really understand both the madness and the genius of what the author is achieving here, we first have to look at the incredibly rigid rules they imposed on themselves to prove these concepts. First, the author strictly imports the init library only. That means absolutely no external math libraries are allowed. Next, there are zero sorries. In Lean-4, that means no skipped proofs whatsoever. None. There are zero new axioms introduced. Every single theorem has to close by kernel, decide, or RFL, which basically means it resolves to an undeniable computable truth. Oh, and the whole thing? It has to build in under 5 seconds. I want you to think of these not just as mathematical constraints, but really as a form of literature, like a poetic constraint. If a theorem passes under these punishingly strict rules, it represents absolute, objective truth within the logic of the system.
The author states this so beautifully. If this regime can hold, then init is not a restricted substrate. It is the honest one. See, by intentionally stripping away all those external libraries and complex crutches, the author truly believes they found the single honest substrate to mathematically map out the nature of reality. It's just a profound commitment to foundational truth.
Okay, so how does this actually operate on a micro level? Well, let's just pick a random .lean file and go deep. So, jumping into the directory, we land right here, perfectly at the intersection of knot theory and determinism. Specifically, we're looking at knottyproblems.lean to see exactly how this system aggregates its logic.
Continuing to pick random files for our deep dive, we open another one and land on unknottheory.lean. The author defines unknot theory as the science of the complement, the open regions of conjecture space inside which reasoning can proceed without paying the universe's energy cost. It's an intensely spatial concept when you think about it. Instead of looking at the knots themselves, we are looking at the negative space. We're looking at the open voids where logic can just operate freely.
And it creates this incredibly brilliant duality. Traditional knot theory is essentially the science of the walls, right? It's the complex, tangled boundaries and falsifications that actually cost energy to compute and navigate. But unknot theory? That's the complement. It's the open, negative space where you can make local rearrangements through zero-cost reasoning. It just perfectly contrasts the known science of structural boundaries with the unknowable but completely navigable science of open voids.
This specific breakthrough is actually captured in a really cool note in the code attributing a Wave 12 insight, which is essentially a late-stage realization in their research, to a figure named Taylor. We have been thinking about knot theory, but not the space between the knots, unknot theory. This metaphor of zero cost is absolutely essential here. It tells us exactly how the author conceptualizes moving through the open spaces of logic. Basically, when you aren't fighting the structural walls of reality, reasoning requires absolutely no computational energy.
Section 2. The Anti-Theorems. Formal acknowledgement of the asymptote.
Okay, this is where the project gets truly fascinating. The author doesn't just use formal code to prove what is, they use it to mathematically prove what cannot be known. The framework formally acknowledges its own limits, treating negative structural claims as first-class theorems right there in the code. Look at these 4 anti-theorems. First, no signature equals the position. This means you can map the shadow of something infinite, but you can never compile the infinite position itself, which the author metaphorically likens to the position of God. Second, boundary information is mathematically incomplete. Third, converging multiple vocabularies still won't close that position. And fourth, the ultimate operational mesh hypothesis of reality? It cannot be internally derived from the calculus itself. The system is rigorously mathematically proving its own boundaries.
The author elegantly maps all of this out for us into 3 very clear buckets. Step 1, what is closed? Things like the cost algebra category and math physics dimension agreement, those are formally locked in. Step 2, what is open but knowable? These are things like specific physical constants that the framework can eventually compute. And step 3, what is structurally unknowable? The infinite position itself. Now, even if the math here sounds a bit dense, the core takeaway is beautiful. The framework gives us the exact shape of the void, but explicitly denies us the content.
Which leaves us with a pretty massive, profound final thought to take away from this explainer on unknot theory and topological code. What happens to our entire understanding of the universe when we finally hit the mathematical limit of computation? And instead of guessing, we must formally and rigorously map out the unknowable. It flips our perspective entirely, doesn't it? Instead of trying to calculate the infinite, maybe our greatest computational achievement will simply be defining the exact shape of the space it leaves behind. Think about that.